The nearest star to our Sun is 4.24 light-years away. That sounds close. It is not. If you climbed aboard the fastest spacecraft humanity has ever built and pointed it at that star, you would arrive in roughly 73,000 years. Your bones would be dust before the ship crossed even 1% of the distance, yet every generation dreams the same dream. Surely we can build something fast enough to get a human being to another star and back within a single lifetime. The physics says otherwise. The energy required, the speeds demanded, the biological limits of the human body, every variable conspires against the dream. Today we will calculate exactly what it would take and discover why the answer is far more brutal than most people imagine. If you enjoy deep explorations of the hardest questions in science and space, consider hitting that like button and subscribing. It genuinely helps this channel keep going. Now, get yourself comfortable, let's begin. Every civilization that has ever looked upward has asked the same question. Can we go there? The Polynesians crossed the Pacific in wooden canoes guided by stars they could not name in any modern catalogue. The Europeans crossed the Atlantic without knowing what lay on the other side. The Americans strapped human beings to columns of burning kerosene and hurled them at the moon. In every case, the distance seemed impossible until someone proved otherwise. And in every case, the people who doubted were reasonable. The ocean was too wide. The void was too cold. The moon was too far. They were wrong each time. So when someone today asks whether a human being could travel to another star and arrive within a single lifetime, the optimist in all of us wants to believe the pattern will repeat. Surely, with enough time and ingenuity, we will find a way. But interstellar space is not the Pacific Ocean. It is not the Atlantic. It is not even the 250,000-mile gap between Earth and the Moon. Interstellar space operates on a scale so far beyond every previous frontier that comparing it to earlier voyages is not just misleading. It is mathematically absurd. The distance between our Sun and the nearest neighbouring star is so large that it breaks every analogy we attempt, mocks every intuition we carry, and punishes every assumption we make about what faster and farther should mean. This is not a problem of will. It is not a problem of funding. It is a problem of physics, and physics does not negotiate. The question we are exploring today sounds deceptively simple. Could a human being leave Earth, travel to another star, and arrive while still alive? Not in science fiction, not in theory, in practice, using real distances, real speeds, real energy, and real biological limits. To answer it honestly, we need to begin with the destination. The nearest star to our Sun is called Proxima Centauri. It is a dim red dwarf, far too faint to see with the naked eye despite being our closest stellar neighbour. It sits in the constellation Centaurus, visible only from the southern hemisphere, and it is part of a triple star system called Alpha Centauri. The other two members of that system, Alpha Centauri A and Alpha Centauri B, are both Sun-like stars that orbit each other as a binary pair. Proxima Centauri orbits that pair at a much greater distance, taking roughly 550,000 years to complete a single loop. This system is not just the closest collection of stars, it is increasingly one of the most scientifically interesting targets in our stellar neighbourhood. Proxima Centauri hosts at least 2 confirmed planets. Proxima Centauri b is roughly Earth-sized and orbits within the star's habitable zone, the region where liquid water could theoretically exist on a planet's surface. It was discovered in 2016 by the European Southern Observatory. A second planet, Proxima Centauri d, was confirmed in 2025 by the NIRPS instrument. It is one of the lightest exoplanets ever detected by radial velocity, with a mass only about a quarter that of Earth. A third candidate, Proxima Centauri c, was proposed as a possible gas dwarf orbiting farther out, but observations published in 2025 by the same NIRPS team were unable to confirm it. As of now, evidence for Proxima c remains inconclusive at best. The larger stars in the system are drawing attention too. In August of 2025, astronomers using the James Webb Space Telescope announced strong evidence for a candidate giant planet orbiting Alpha Centauri A. Using the telescope's mid-infrared instrument and a coronagraph to block the star's light, the team detected a faint point source roughly 2 times the Earth-Sun distance from Alpha Centauri A. Follow-up observations in February and April of 2025 did not redetect the object, but computer simulations of millions of possible orbits showed that in about half the scenarios, the planet would have moved too close to the star to be visible during those follow-up windows. If confirmed, this candidate would be a gas giant roughly the mass of Saturn, orbiting within Alpha Centauri A's habitable zone. It would be the closest habitable zone planet ever found orbiting a Sun-like star. The planet itself would not support life as we know it, but any moons it might possess could be another matter entirely. So the target is real. The nearest star system contains confirmed planets and tantalizing candidates. There are reasons to want to go there that extend far beyond curiosity. The question is whether going there is physically possible within a single human life. To answer that, we need to confront the distance. And the distance is where the dream begins to fracture. Proxima Centauri is 4.24 light-years from Earth. Alpha Centauri A and B are slightly farther at 4.37 light-years. A light-year is the distance that light travels in 1 year, moving at approximately 186,000 miles per second. 1 light-year equals roughly 5.88 trillion miles. Multiply that by 4.24. The distance to Proxima Centauri is approximately 24.9 trillion miles. Written out in full, that number is 24,900 billion miles. If you prefer kilometers, it is roughly 40 trillion. These numbers are so large that they resist comprehension. The human brain did not evolve to process distances on this scale. We can say the words, but we cannot feel their weight. So let us try to build a model that forces the scale into something our minds can hold. Shrink the sun down to the size of a basketball. At this scale, Earth becomes a tiny grain of sand orbiting about 26 yards away. Jupiter becomes a marble roughly 135 yards from the basketball. Neptune, the outermost planet, sits about half a mile away. The entire solar system, from the Sun to the orbit of Neptune, fits within a circle roughly 1 mile in diameter. This is the realm humanity has actually explored with spacecraft. Voyager 1, our farthest probe, launched in 1977, is currently at a distance equivalent to about 2.5 miles from the basketball on this scale. It has been travelling for nearly 50 years and it has covered 2.5 miles. Now, where is Proxima Centauri on this model? It is not across the room. It is not across the city. It is not across the state. Proxima Centauri, at basketball sun scale, is roughly 4,400 miles away. That is approximately the distance from New York City to Honolulu, Hawaii. The entire solar system is a circle 1 mile wide. The nearest star is in Hawaii. And Voyager, our fastest and farthest explorer, has walked 2.5 miles in 50 years. Sit with that for a moment. The interstellar gulf is not a larger version of the distances we have crossed before. It is a categorically different kind of distance. It is not 10 times farther than what we have achieved. It is not 100 times farther. It is thousands of times farther than anything a human-built object has ever traversed. And we are talking about the nearest star, the closest one, the absolute minimum distance to any other sun in the galaxy. Every other star is farther. Most are incomprehensibly farther. Now let us add time. The question is not just whether we can cross this distance, but whether we can cross it within a human lifetime. So we need to define what one lifetime means in practical terms. Average human life expectancy in developed countries today is roughly 78 to 82 years. Let us be generous. Assume medical advances push the healthy human lifespan to 100 years. Assume the traveller departs at age 25. That gives a maximum travel window of about 75 years. though realistically the window is shorter if you want the astronaut to arrive in any condition to function. So, the question sharpens. Can a spacecraft carry a living human being across 25 trillion miles within roughly 50 to 75 years? The first instinct is to look at what we have already built. Our fastest interstellar-capable spacecraft is Voyager 1. Launched in 1977 on a mission to study Jupiter and Saturn, Voyager 1 used gravitational slingshots from those giant planets to accelerate to its current velocity. It is travelling at approximately 17 kilometers per second relative to the Sun. That is about 38,000 miles per hour. In everyday terms, that is extraordinarily fast. A commercial airliner flies at around 550 miles per hour. A bullet from a high-powered rifle travels at roughly 2,000 miles per hour. Voyager 1 is moving 19 times faster than a rifle bullet. It is the fastest object humanity has ever sent, on a sustained trajectory away from the Sun, and it is worth pausing to appreciate what that means. Voyager 1 is a genuine triumph of human engineering. It was built in the 1970s with technology less powerful than what now sits inside a basic digital watch. Its onboard computer has roughly 69 kilobytes of memory. Its radio transmitter operates at about 23 watts, less than a refrigerator light bulb. And yet it is still functioning, still transmitting data, still responding to commands from Earth across a distance so vast that its signals, travelling at the speed of light, take more than 23 hours to reach us. Every instruction sent to Voyager 1 arrives almost a full day after transmission. Every response takes another day to come back. The engineers who communicate with it are conducting a conversation with a 47-hour round-trip delay, reaching across a void so deep that light itself needs nearly a full rotation of the Earth to bridge it. By November of 2026, Voyager 1 is projected to reach a distance of 1 light day from Earth, a milestone that has never been reached by any human-made object. It is, by any reasonable measure, the single most distant thing our species has ever created, and it is nowhere close to another star. At Voyager 1's speed, how long would it take to reach Proxima Centauri? The answer is approximately 73,000 years. That number is not a rough estimate meant to sound dramatic. It is a straightforward calculation based on confirmed velocity data from NASA's Jet Propulsion Laboratory. Voyager 1 covers roughly 1 light-year every 17,000 to 18,000 years. The distance to Proxima Centauri is 4.24 light-years. The arithmetic is merciless, 73,000 years. To put that in perspective, the entirety of recorded human history spans roughly 5,000 years. The agricultural revolution began approximately 12,000 years ago. Anatomically modern humans have existed for about 300,000 years. If Voyager 1 had departed for Proxima Centauri when Homo sapiens first appeared on Earth, it would not have arrived yet. It would still have more than halfway to go, but let us make 73,000 years feel less abstract. Rewind the clock on Earth by that amount. 73,000 years ago, modern humans shared the planet with Neanderthals. Homo sapiens had not yet migrated out of Africa in large numbers. There were no cities, no agriculture, no writing, no metal tools. The most advanced technology on Earth was a sharpened stone. The concept of a wheel would not be invented for another 68,000 years. If someone had launched a Voyager-class spacecraft from Earth at that moment, pointed at Proxima Centauri, it would be arriving approximately now. Every single event in the entire human story, the development of language, the rise of every empire, every war, every revolution, every invention from fire to fusion reactors, all of that would fit inside the travel time. The ship would depart from a world of stone tools and arrive at a world of space telescopes and particle accelerators. And the people who launched it would be separated from the people who received it by a gulf of time so vast that the two civilizations would share almost nothing except their species. That is what 73,000 years means. It is not a number. It is the entire arc of human development, compressed into the transit time of a single spacecraft crossing the smallest interstellar gap in the galaxy. And Voyager 1 is not even pointed at Proxima Centauri. It is headed in a different direction entirely, toward the constellation Ophiuchus. It will pass within 1.7 light-years of an obscure star called AC plus 79, 3888, in roughly 40,000 years. It will never reach Alpha Centauri. No existing spacecraft will. No spacecraft currently under construction will. No spacecraft in any approved mission plan will. This is the first and most important fact about interstellar travel. At the speeds we can currently achieve, reaching even the nearest star takes longer than civilizations last. The fastest thing we have ever built is not 1% of 1% as fast as it would need to be. Let us verify this with a different spacecraft. New Horizons, launched in 2006, was the fastest vehicle ever launched from Earth at the time. It departed at a speed of roughly 16.26 kilometers per second relative to Earth. After a gravity assist from Jupiter, its heliocentric speed reached varying values, but its current speed is approximately 14 kilometers per second. That is actually slower than Voyager 1, because Voyager 1 received more favorable gravity assists. New Horizons would take even longer to cross interstellar distances. Parker Solar Probe, launched in 2018, holds the record for the fastest human-made object relative to the Sun, reaching speeds above 190 kilometers per second during its closest solar approaches. But that speed is achieved only during brief perihelion passes, when the probe is falling deep into the Sun's gravitational well. It is not a sustained velocity. Parker Solar Probe is not on an escape trajectory from the solar system. It cannot be meaningfully compared to interstellar transit speeds because its velocity is borrowed from the Sun's gravity and returned on each orbit. It is like pointing to a skydiver in freefall and claiming humans can fly at terminal velocity. The speed is real, but the context makes it irrelevant to the interstellar question. So let us set the benchmark clearly. The fastest sustained speed humanity has achieved for an object leaving the solar system is roughly 17 kilometers per second, represented by Voyager 1. At that speed, the nearest star is 73,000 years away. A human lifetime is 80 years. The ratio between what we need and what we have is roughly 900 to 1. We are not close. We are not in the neighborhood of close. We are off by nearly 3 orders of magnitude. This is often the point where someone says, well, technology improves. We went from horse-drawn carriages to jet aircraft in a century. Surely we will find a way to go faster. And that instinct is understandable. But it runs into a wall that horse-drawn carriages never faced. The energy required to accelerate a physical object to interstellar speeds is not a technology problem in the way that building a jet engine was a technology problem. It is a physics problem, governed by equations that do not change with time. And the numbers those equations produce are staggering. But before we get to the energy, it helps to understand exactly how fast we would need to go. 4.24 light-years in 80 years requires an average speed of roughly 5.3% of the speed of light. Call it 5% for simplicity. 5% of the speed of light is approximately 15,000 kilometers per second. That is around 33.5 million miles per hour. Compare this to Voyager 1's 38,000 miles per hour. We would need to travel nearly 900 times faster than the fastest interstellar-capable object ever built. But 80 years is generous. It assumes the astronaut departs at birth and arrives on their deathbed. More realistically, the journey should take no more than 40 to 50 years, so the traveller arrives with decades of productive life remaining. Crossing 4.24 light-years in 40 years requires roughly 10% of the speed of light. 10% of light speed is just under 30,000 kilometers per second. That is 67 million miles per hour, roughly 1,760 times Voyager 1's speed. If you want to be truly ambitious and cross the distance in 20 years, which would allow for a potential round trip within a human lifetime, you need roughly 20% of the speed of light. That is 60,000 kilometers per second, 134 million miles per hour, 3,500 times the speed of Voyager 1. These numbers deserve attention because they reveal something important about the nature of the interstellar problem. The nearest star is not impossibly far in the sense that we cannot point at it and describe the route. It is impossibly far in the sense that closing the distance within a human lifespan demands speeds that are qualitatively different from anything we have ever achieved. We are not talking about incremental improvements. Going from 38,000 miles per hour to 67 million miles per hour is not like going from a propeller airplane to a jet. It is like going from a bicycle to a significant fraction of the speed of light. The engineering challenges do not scale linearly. They scale exponentially. Every factor of 2 increase in speed requires roughly a factor of 4 increase in kinetic energy. Every factor of 10 increase in speed requires a factor of 100 increase in energy. The cost of speed rises as the square of velocity, and at relativistic fractions, it rises even faster, because the mass of the vehicle effectively increases as it approaches light speed. This is why the interstellar distance problem cannot be solved simply by building a bigger rocket. There is a fundamental relationship between mass, speed, and energy that governs what is possible, and for interstellar velocities, that relationship produces numbers that dwarf the energy output of entire civilizations. Let us anchor this with one more concrete reference point. Voyager 1 has been traveling for nearly 50 years. As of March 2026, it is approximately 172.6 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. So Voyager 1 is roughly 16 billion miles from Earth. That sounds like an immense distance, and it is. Light from the Sun takes about 24 hours to reach Voyager 1. In fact, in November of 2026, Voyager 1 is projected to reach a distance of 1 light day from Earth. 1 light day, the distance light covers in 24 hours. The distance to Proxima Centauri is 4.24 light years. A light year contains 365.25 light days. 4.24 light years is roughly 1,549 light days. Voyager 1, after nearly half a century of travel, has covered 1 light day. It has traversed less than 0.1% of the distance to the nearest star. A journalist writing about Voyager 1 recently framed it with devastating clarity. The probe has been a spectacular success by every engineering and scientific measure, and it has barely left the neighbourhood. That framing captures the essence of the interstellar distance problem better than any number can. We are not failing to cross the gap. We have not even meaningfully started. The tools we possess today, the pinnacle of human engineering, the product of decades of effort and billions of dollars, can barely scratch the surface of interstellar space. And the nearest star sits on the other side of a distance so vast that our fastest machine will not bridge it in less than 1,000 human lifetimes. This is what makes the question so powerful and so painful. The target is tantalizingly close by cosmic standards. Proxima Centauri is not across the galaxy. It is right next door. Astronomers can study its planets in remarkable detail. The JWST is already imaging candidate worlds in the Alpha Centauri system. We know more about the nearest stars than any previous generation could have dreamed. We can almost taste the destination. We simply cannot reach it. The stars visible on a clear night feel close. They look like they are right there, scattered across the darkness just above the treetops. Ancient humans believed they were attached to a crystalline sphere that surrounded the Earth, close enough to touch if you could only climb high enough. Modern humans know better. We know those lights are other suns, burning at distances measured in trillions of miles. But knowing is not the same as feeling. Our intuition still whispers that the nearest star should be reachable. It is, after all, the nearest one. How far could it really be? 25 trillion miles. 73,000 years at our best speed. Less than 0.1% crossed after 50 years of flight. That is how far. And yet the dream persists. Not because it is naive, but because the destination is real and the reasons to go are profound. There may be planets there. There may be worlds with atmospheres and oceans. There may be moons orbiting gas giants in habitable zones. The Alpha Centauri system is not a barren waypoint. It is a legitimate scientific target, possibly the most important one outside our own solar system. The desire to go there is not fantasy. It is the natural extension of the same impulse that drove humans across every ocean and to the surface of the moon. But desire is not capability. And the gap between what we want and what physics allows is not closing at any meaningful rate. Chemical rockets cannot do it, ion drives cannot do it, solar sails at their current scale cannot do it. Every propulsion system that exists today produces speeds so far below interstellar requirements that they might as well be standing still. The question, then, is not whether we want to go. Of course we want to go. The question is whether any conceivable technology could close the gap, whether there is some engine, some energy source, some method of acceleration that could push a human being across 25 trillion miles of vacuum before their heart stops beating. To answer that, we need to move beyond distance and talk about speed. Real speed. The kind of speed that would actually matter. And when we start calculating what those speeds demand in terms of energy, fuel and engineering, the picture becomes far darker than the distance alone suggests. We established the destination. We measured the distance. We proved that our fastest existing spacecraft would need 73,000 years to reach the nearest star. Now we need to confront the more dangerous half of the problem. What speeds are actually required, and what happens to physics and engineering when you try to achieve them? The arithmetic is straightforward. To cross 4.24 light years in 80 years, a spacecraft must average about 5% of the speed of light. To do it in 40 years, roughly 10%. In 20 years, 20%. These percentages sound modest. 5%, 10%, 20%. They sound like fractions of something, rather than enormous quantities in their own right. This is an illusion created by the absurd magnitude of light speed itself. When you convert these percentages into actual velocities, the numbers become violent. 10% of the speed of light is approximately 29,979 kilometers per second. In miles per hour, that is roughly 67 million. 67 million miles per hour. For context, the International Space Station orbits Earth at about 17,500 miles per hour. A spacecraft travelling at 10% of light speed would cross the distance from Earth to the Moon in about 13 seconds. It would reach Mars at its closest approach in roughly half an hour. It would cross from the Sun to Pluto in roughly 2.5 days. These are speeds at which the solar system shrinks to the scale of a small town. Distances that take our best probes years to cover would vanish in an afternoon. But reaching those speeds requires energy, and this is where the problem transforms from ambitious to nearly impossible. Let us begin with what we know. The fundamental relationship between speed and energy is one of the oldest equations in physics. Kinetic energy equals 1/2 times mass times velocity squared. The critical word is squared. If you double the speed of an object, you do not double the energy required. You quadruple it. Triple the speed, and you need 9 times the energy. Increase the speed by a factor of 1,000, as interstellar travel demands compared to our current best, and you need 1,000,000 times more energy. This is not a negotiable feature of the universe. It is baked into the structure of classical mechanics, and at relativistic speeds, the situation becomes even worse, because special relativity adds an additional mass increase that drives the energy requirement toward infinity as you approach light speed. For interstellar travel, this squaring relationship is devastating. Going from Voyager's 17 kilometers per second to the 30,000 kilometers per second needed for 10% of light speed is an increase of roughly 1,760 times. Squaring that ratio gives an energy increase of approximately 3.1 million times. A spacecraft that needs 3 million times more energy than Voyager 1 carried is not an engineering challenge. It is a civilization-scale energy problem. But it gets worse. Voyager 1 does not carry its own fuel for sustained propulsion. It was accelerated by chemical rockets during launch, and then boosted by gravitational slingshots from Jupiter and Saturn. Those gravity assists were free, borrowed from the orbital energy of giant planets. An interstellar spacecraft cannot rely on gravity assists to reach 10% of light speed. There are no giant planets conveniently placed along the route to Alpha Centauri. The ship must carry or receive its own energy, and this is where the rocket equation enters the picture and makes everything dramatically harder. The Tsiolkovsky rocket equation is one of the most important and most unforgiving relationships in spaceflight. It describes the fundamental connection between a rocket's exhaust velocity, the ratio of its initial mass to its final mass, and the change in velocity it can achieve. In plain language, it says that the speed a rocket can reach depends on how fast it throws material out the back and how much of the rocket's total mass is fuel versus payload. The equation is logarithmic, which means that achieving higher speeds requires exponentially more fuel relative to the payload. This exponential scaling is the single biggest obstacle to interstellar travel. Consider chemical rockets first. The best chemical rocket engines burning liquid hydrogen and liquid oxygen achieve exhaust velocities of roughly 4.5 kilometers per second. To reach even 1% of the speed of light using chemical propulsion alone, without gravity assists, the fuel-to-payload ratio required by the rocket equation is not 10:1. It is not 100:1. It is not 1,000,000:1. It is a number so preposterously large that it exceeds the mass of the observable universe. You could convert every atom in every galaxy into rocket fuel, and it would still not be enough to push a single kilogram to 1% of light speed using chemical propulsion. This is not an exaggeration for dramatic effect. It is the direct output of the rocket equation when you plug in chemical exhaust velocities and interstellar target speeds. Chemical rockets are categorically incapable of interstellar travel. They cannot even approach the threshold. The gap is not something that better engineering can close because the limitation is thermodynamic, not technological. So chemical propulsion is eliminated entirely. What about nuclear options? Nuclear thermal propulsion, where a nuclear reactor heats a propellant like hydrogen and expels it at high speed, can achieve exhaust velocities roughly double those of chemical rockets. Around 9 to 10 kilometers per second. This is better, but the rocket equation remains merciless. Doubling the exhaust velocity does not halve the fuel ratio. It reduces it, but the ratio for interstellar speeds is still absurdly large. Nuclear thermal rockets are excellent for getting around the solar system faster. They are useless for reaching the stars. Nuclear pulse propulsion is a different concept entirely, and the first one that begins to approach interstellar viability, at least on paper. The idea originated in the late 1950s with Project Orion, a study funded initially by DARPA and later by the US Air Force. The concept was breathtaking in its audacity. A spacecraft would carry thousands of small nuclear bombs. It would eject them one at a time behind the ship, detonate them, and ride the shockwave using a massive pusher plate mounted on shock absorbers at the rear of the vessel. Each detonation would deliver a pulse of acceleration. Over time, the cumulative velocity change could become enormous. Freeman Dyson, the physicist who worked on the project, estimated that an Orion-type vessel could theoretically reach 3 to 5% of the speed of light. At 3%, the trip to Proxima Centauri would take roughly 140 years. At 5%, about 85 years. This is within striking distance of one human lifetime, though barely, and only if the traveller departed young and the upper speed estimates proved achievable. But Orion was never built. The Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear detonations in space, effectively killing the project. Beyond the legal barriers, the engineering challenges were formidable. The pusher plate would need to withstand repeated nuclear blasts at close range. The shock absorber system would need to convert violent impulses into smooth acceleration tolerable by a crew. The ship itself would be enormous. potentially weighing tens of thousands of tons when fully loaded with its nuclear charges, and the exhaust would be intensely radioactive, creating a trail of nuclear fallout through the solar system during the acceleration phase. Orion was a concept that could theoretically work, but that no society has chosen to build, and for reasons that extend well beyond engineering. Fusion propulsion represents the next step. If a spacecraft could harness the same nuclear fusion reactions that power the Sun, it could theoretically achieve exhaust velocities of several thousand to tens of thousands of kilometers per second, depending on the specific reaction used. The most commonly discussed reaction for interstellar propulsion is deuterium-helium-3 fusion, which produces charged particles that can be directed magnetically, yielding very high exhaust velocities without the radiation problems of deuterium-tritium fusion. The British Interplanetary Society explored this concept in the 1970s with Project Daedalus, one of the most detailed interstellar mission studies ever conducted. Daedalus was designed as an uncrewed flyby probe targeted at Barnard's star, roughly 6 light-years away. The vehicle would use inertial confinement fusion, igniting small pellets of deuterium and helium, 3 with electron beams 250 times per second. The probe would accelerate for about 2 years, reaching approximately 12% of the speed of light, then coast for roughly 46 years before flying past its target. Total mission time was about 50 years. The probe itself would weigh approximately 54,000 metric tons at launch, of which 50,000 tons was fuel. It would carry no crew and could not decelerate. Daedalus remains one of the most credible interstellar mission designs ever produced. It demonstrated that, in principle, a fusion-powered probe could reach another star within a human lifetime. But it also revealed the staggering scale of the engineering involved. 50,000 tons of helium-3 fuel, a substance that barely exists on Earth. The study proposed mining it from the atmosphere of Jupiter, an endeavour that would itself require a spacefaring infrastructure far beyond anything we possess. And this was for a probe, not a crewed ship. No humans, no life support, no radiation shielding, no deceleration. Just a package of instruments flying past another solar system at 12% of light speed, taking pictures during a brief encounter window and transmitting data back to Earth over the following years. A follow-up study called Project Longshot, completed in 1988 by the US Naval Academy and NASA, proposed a smaller fusion probe to Alpha Centauri, but with lower performance and a century-long travel time. More recently, Project Icarus, initiated in 2009 by the British Interplanetary Society and the Tau Zero Foundation, revisited the Daedalus concept with updated physics and engineering. Each study confirmed the same basic conclusion. Fusion propulsion could theoretically push an uncrewed probe to interstellar speeds. But the fuel requirements are enormous. The engineering is beyond our current capability, and no one has yet built a sustained, controlled fusion reactor of any kind, let alone one compact and powerful enough to propel a spacecraft. As of 2026, the most advanced fusion experiments on Earth, facilities like ITER in southern France, are still years away from achieving sustained net energy gain in a stationary reactor the size of a building. Shrinking that technology into a flight-rated engine that fits on a spacecraft, operates reliably for years, and produces enough thrust to matter is a leap measured not in decades, but possibly in centuries of further development. Now consider antimatter. Antimatter is the most energy-dense substance permitted by physics. When matter and antimatter meet, they annihilate completely, converting 100% of their combined mass into energy according to Einstein's famous equation. 1 kilogram of antimatter annihilating with 1 kilogram of matter releases approximately 1.8 times 10 to the 17th joules of energy. That is roughly equivalent to a 43 megaton nuclear weapon. For perspective, that single kilogram pair annihilation releases more energy than the annual output of roughly half a dozen large power plants combined. An antimatter rocket, if it could be built, would have the highest possible specific impulse of any propulsion system, because the exhaust velocity approaches the speed of light. A few hundred kilograms of antimatter could theoretically accelerate a small spacecraft to a significant fraction of light speed. On paper, antimatter propulsion is the most promising route to interstellar travel. The problem is manufacturing and storage. As of today, humanity produces antimatter in vanishingly small quantities, measured in nanograms per year, at costs that defy comprehension. CERN, the European Organization for Nuclear Research, has produced and trapped small numbers of antihydrogen atoms for research purposes. The total amount of antimatter ever produced by all of humanity's particle accelerators combined would not power a light bulb for a fraction of a second. Estimates suggest that producing a single gram of antimatter with current technology would cost on the order of tens of trillions of dollars and require decades of continuous operation of existing facilities. An interstellar mission might need kilograms. The production cost would exceed the gross domestic product of the entire planet by orders of magnitude. Storage is equally daunting. Antimatter annihilates on contact with any normal matter. It must be confined in perfect vacuum and held in place by magnetic fields, a technique called a penning trap for charged antiparticles. Storing milligrams is a laboratory achievement. Storing kilograms is currently science fiction. A containment failure would not merely end the mission. It would release energy equivalent to a thermonuclear weapon. So, antimatter propulsion is physically valid but practically inaccessible. It is not forbidden by physics. It is forbidden by economics, manufacturing capability, and material science. Perhaps in centuries, breakthroughs in antimatter production could change this calculus, but no credible near-term or medium-term technology roadmap leads to antimatter-powered spacecraft. This brings us to one more concept that deserves serious attention because it attempted to sidestep the fuel problem entirely. Breakthrough Starshot, announced in 2016 by physicist and investor Yuri Milner alongside Stephen Hawking, proposed using ground-based lasers to accelerate ultralight spacecraft to 20% of the speed of light. The idea was elegant in its simplicity. Instead of carrying fuel, the spacecraft would unfurl a thin reflective sail a few meters across. An array of powerful lasers on Earth's surface would focus a beam on the sail, pushing it with radiation pressure. The spacecraft, called a starship, would weigh only a few grams. At that mass, the energy required for acceleration becomes manageable, at least compared to accelerating a crude vessel. At 20% of light speed, a starship would reach Alpha Centauri in about 20 years. It would fly past the system, snap images of any planets, and transmit data back to Earth using a tiny onboard laser. The return signal would take roughly 4.3 years to arrive. Total time from launch to data receipt, approximately 25 years. Within a single human lifetime, comfortably. But Breakthrough Starshot faced enormous technical challenges. The laser array would need to produce roughly 100 gigawatts of power, focused with extraordinary precision on a sail the size of a small room at distances of millions of kilometers. The sail would need to survive being hit by that much energy without melting. The acceleration would be brutal, roughly 10,000 times the force of gravity, applied for approximately 10 minutes. The gram-scale spacecraft would need to carry cameras, power systems, and a communication laser capable of transmitting data across 4 light-years, and critically, the probe could not decelerate. It would fly past Alpha Centauri at 20% of light speed, getting perhaps a few hours of close observation before the system receded into the distance. As of 2025, Breakthrough Starshot is on indefinite hold. A report in Scientific American in September of that year detailed how the project had spent only about $4.5 million of its pledged $100 million budget across roughly 30 research contracts over 9 years. Key personnel declined interviews. The future of the program was described as murky. Laboratory experiments at Caltech in 2025 did successfully measure radiation pressure on tiny light sail prototypes for the first time, confirming the basic physics of laser propulsion. But moving from a 50 nanometer silicon nitride membrane in a laboratory to a functional interstellar sail capable of surviving 100 gigawatts of laser power remains a vast engineering gap. And here is the essential point about Breakthrough Starshot, the detail that matters most for our central question. Even if it worked perfectly, it would not send a human being to another star. It would send a chip the size of a postage stamp. The mass difference between a gram-scale probe and a crude interstellar vehicle is not a factor of 10 or 100. A crude spacecraft, carrying even a minimal crew with life support, radiation shielding, food, water, air, medical supplies, and the structural mass to hold it all together, would weigh at minimum tens of thousands of kilograms. More realistic estimates for a crude interstellar vessel run to hundreds of thousands or millions of kilograms. The ratio between a 1-gram star chip and a 100,000 kilogram crude vessel is 100 million to 1. Energy scales with mass. If accelerating 1 gram to 20% of light speed requires a 100 gigawatt laser firing for 10 minutes, then accelerating 100,000 kilograms to the same speed would require a laser array with a power output 10 trillion times greater, or an equivalent amount of energy delivered through some other means. That is not an engineering problem. That is a statement about the total energy output of a civilization. To put it in concrete terms, the kinetic energy of a 100,000 kilogram spacecraft traveling at 10% of the speed of light is approximately 4.5 times 10 to the 19th joules. The total annual energy consumption of human civilization is roughly 5.8 times 10 to the 20th joules. So the kinetic energy alone, not counting the inefficiencies of any propulsion system, represents roughly 8% of humanity's annual energy use for a single launch, and this calculation ignores the fuel mass problem entirely. If the spacecraft carries its own fuel, the initial mass balloons by factors of hundreds or thousands, and the energy required rises accordingly. If you also want to decelerate at the destination, the energy roughly doubles again. This is the wall, not a wall of imagination or ambition or funding, a wall of physics. The energy required to push a human-carrying spacecraft to interstellar speeds is so enormous that it challenges the output capacity of entire planetary civilizations. And even if you could generate that energy, you would still need to solve the problem of how to apply it. Chemical engines cannot. Nuclear thermal engines cannot. Fusion engines might, theoretically, in some far future, but no working prototype exists. Antimatter engines could, but the fuel does not exist in usable quantities. External laser propulsion works only for objects lighter than a coin. Every proposed solution runs into the same fundamental bottleneck. Either the fuel-to-payload ratio is impossibly large, or the energy source does not exist at the required scale, or the propulsion concept has not been demonstrated even in a laboratory setting. No technology currently under development at any space agency or private company on Earth is designed to accelerate a crude vehicle to even 1% of light speed. The gap between where we are and where we would need to be is not a gap that can be closed by iterating on existing hardware. It requires capabilities that do not exist, and that may not exist for a very long time. Some might point to science fiction staples like warp drives or wormholes. These concepts emerge from theoretical physics but have no experimental support whatsoever. The Alcubierre metric, proposed in 1994, describes a mathematical solution to Einstein's field equations that would allow a bubble of spacetime to move faster than light. But it requires negative energy density, a substance that has never been observed in the quantities needed and may not exist. Traversable wormholes, theoretical tunnels through spacetime, require exotic matter to hold them open, and no experiment has ever produced or detected exotic matter. These ideas are not engineering challenges waiting for funding. They are speculative mathematical constructs with no known path to physical realization. Treating them as future options is indistinguishable from hoping for magic. So let us take stock of where we stand. Chemical propulsion is eliminated. Nuclear thermal propulsion is eliminated. Nuclear pulse propulsion could theoretically reach a few percent of light speed, but has never been tested and faces severe legal, political, and engineering barriers. Fusion propulsion could theoretically reach 10 to 15% of light speed for an uncrewed probe, but requires technology that does not yet exist and fuel sources that would need to be mined from other planets. Antimatter propulsion is the theoretical gold standard, but cannot be produced or stored at any meaningful scale. Laser sail propulsion works for gram-scale probes but cannot accelerate human-carrying vessels without energy outputs that exceed current civilization-level capacity. For a crewed mission, every path leads to the same conclusion. The energy required is staggering. The technology required does not exist. The gap between what we can build and what we would need is measured not in years of development, but in fundamental breakthroughs that no one can schedule or guarantee. And yet, for the sake of argument, let us imagine that we solve the propulsion problem. Let us imagine that some future civilization builds an engine capable of accelerating a crewed ship to 10% of the speed of light. The journey to Proxima Centauri would take about 42 years. The crew would depart in their 20s and arrive in their 60s. It is conceivable, just barely within a human lifetime, but reaching 10% of light speed does not end the problem. It reveals a new set of problems that have nothing to do with engines or fuel. Because travelling through interstellar space at 67 million miles per hour introduces hazards that are, in some ways, harder to solve than the propulsion challenge itself. The interstellar medium is not empty. Cosmic radiation does not stop at the edge of the solar system. Dust grains that weigh less than a fleck of pepper carry the kinetic energy of explosives at those speeds. And if you want to actually stop at the destination rather than scream past it at 10% of light speed, you face the single most crippling constraint in all of interstellar mission design. The speed problem does not end with achieving speed. The real nightmare begins when you try to survive it. Imagine you have solved the impossible. Some future civilization has built a propulsion system capable of accelerating a crewed spacecraft to 10% of the speed of light. The engine works. The fuel exists. The launch succeeds. The ship reaches its cruising velocity of roughly 30,000 kilometers per second and begins its 42-year coast toward Proxima Centauri. The crew is young, healthy, and determined. The vessel is stocked with decades of supplies. Everything that could be engineered has been engineered. Now the real problems begin. Because the space between stars is not empty, and moving through it at 67 million miles per hour turns the gentlest environment in the universe into a killing field. Start with the interstellar medium. The void between stars contains matter, not much, but some. On average, the interstellar medium in our region of the galaxy holds roughly 1 atom per cubic centimetre. Almost all of those atoms are hydrogen, the lightest element. At rest, a single hydrogen atom is utterly harmless. It weighs approximately 1.67 times 10 to the negative 27 kilograms. You could pass through trillions of them without noticing. But physics does not care about an atom's mass at rest. Physics cares about relative velocity. And when a spacecraft is moving at 10% of the speed of light, every stationary hydrogen atom in its path becomes a projectile travelling from the ship's frame of reference at 30,000 kilometers per second. At that relative speed, a hydrogen atom carries kinetic energy measured in mega-electron volts. Each individual atom acts like a cosmic ray particle. The flux of these pseudo-cosmic rays depends on the density of the interstellar medium and the speed of the spacecraft. At 10% of light speed, the forward-facing surface of the ship would be bombarded by roughly 3 times 10 to the 13 hydrogen atoms per square meter per second, each one carrying enough energy to penetrate biological tissue and damage DNA. The cumulative radiation dose from this bombardment is severe. Multiple studies have estimated that a spacecraft travelling at 10% of the speed of light through the average interstellar medium would subject its forward-facing surfaces to radiation levels that would be lethal to unshielded humans within days to weeks. This is not radiation from a distant source like a supernova or a pulsar. This is radiation generated by the ship's own motion. The faster you go, the worse it gets, because both the energy per particle and the number of impacts per second increase with velocity. At 20% of light speed, the dose rate roughly quadruples compared to 10%, because the energy per particle doubles and the number of encounters per second also doubles. Shielding against this radiation is theoretically possible but practically enormous. The most straightforward solution is a physical shield, a thick slab of material mounted on the front of the spacecraft to absorb incoming particles before they reach the crew compartment. Hydrogen atoms at mega-electron-volt energies are stopped by relatively modest amounts of material. A few centimeters of aluminum or a meter or so of water or polyethylene would absorb most of them, but the shield must cover the entire forward cross-section of the spacecraft, and it must survive decades of continuous bombardment without degrading. More critically, the shield adds mass, and every kilogram of shielding mass must also be accelerated to 10% of light speed, compounding the fuel problem we explored earlier. Some mission designers have proposed using magnetic deflection instead, generating a powerful magnetic field ahead of the spacecraft to sweep charged particles away from the hull, similar to how Earth's magnetosphere protects us from the solar wind. This could work for ionized hydrogen, which constitutes most of the interstellar medium. But generating a magnetic field strong enough to deflect particles at these energies over a sufficient volume of space requires superconducting magnets of extraordinary power, drawing energy from the ship's reactor for the entire duration of the voyage. Neutral atoms would pass through the magnetic field unaffected, requiring a supplementary physical shield regardless. There is no clean solution. Every shielding approach adds mass, complexity, and energy draw to a spacecraft that is already operating at the absolute limit of what physics permits. But hydrogen atoms are not the worst threat in interstellar space. Dust is. The interstellar medium contains small, solid particles, grains of silicate, carbon, and ice, ranging in size from nanometers to micrometers. The density of these grains is much lower than the density of hydrogen atoms, perhaps 1 grain per 10,000 cubic meters in the diffuse interstellar medium near the Sun. But the energy carried by a single grain impact at relativistic speed is staggering. Consider a grain of interstellar dust weighing 1 microgram, 1/1,000,000th of a gram. At rest, this particle is invisible to the naked eye. You could fit thousands of them on the head of a pin. At 10% of the speed of light, this single grain carries a kinetic energy of approximately 4.5 times 10 to the 5th joules. That is 450 kilojoules. For comparison, a standard military hand grenade releases roughly 600 kilojoules upon detonation. A single microgram dust grain at 10% of light speed strikes with nearly the energy of a hand grenade. One tiny, invisible particle, delivering an explosion you could hear from across a building. At 20% of light speed, the energy quadruples to roughly 1.8 megajoules per microgram grain. That is equivalent to detonating nearly half a kilogram of TNT, concentrated into a single microscopic impact on a surface area smaller than a pinhead. The frequency of such impacts depends on the path the spacecraft takes and the local dust density. In the relatively clear interstellar medium near the Sun, a spacecraft might encounter 1 microgram-sized grain every few years to decades. Smaller grains are far more common and still carry enormous energy at relativistic speeds. Nanogram-scale particles would strike the ship many times per year, each impact releasing energy comparable to a rifle bullet or more. Over a 42-year voyage, the cumulative damage could be catastrophic. Protecting against dust impacts requires either an extremely thick and massive forward shield, capable of absorbing repeated high-energy strikes without structural failure, or some form of active defense that detects and deflects incoming grains before they reach the hull. Neither technology exists. The shield approach again compounds the mass problem. A slab of material thick enough to absorb thousands of such grenade-equivalent impacts over decades without structural failure would weigh hundreds to thousands of tons, all of which must be accelerated to cruising speed along with the rest of the ship. Active deflection of electrically neutral dust grains at microsecond reaction times is beyond any sensor or actuator technology we can currently envision. Some researchers have proposed flying the spacecraft behind a long, thin, needle-like structure that would vaporize incoming dust grains before they reach the main hull, spreading the impact energy over a longer distance and reducing the peak force. Others have suggested deploying a cloud of sacrificial particles ahead of the ship to intercept dust grains and absorb their energy in empty space. These are creative ideas. None have been tested. None have been validated by engineering analysis at the level required for a mission that will last decades with zero margin for error. The interstellar medium does not care about our ambitions. It is there, sparse but lethal at the speeds interstellar travel demands. Any crewed mission must solve the shielding problem completely, because a single unshielded microgram impact could breach the hull, decompress the crew compartment, and end the mission in seconds. There is no rescue vehicle. There is no abort trajectory. There is no way home if the ship is critically damaged between the stars. The crew would be more isolated than any human beings have ever been or likely ever will be, separated from the nearest help by years of light travel time and decades of physical distance. Now suppose the shielding problem is also solved. The ship has a thick forward shield, the magnetic deflectors are running, the crew is protected from radiation and dust. They are cruising at 10% of light speed, 42 years to Proxima Centauri. The crew was in their mid-20s at departure. They will be in their late 60s upon arrival, tired, aged but alive. The mission is almost complete, except it is not, because the ship is still moving at 30,000 kilometers per second, and Proxima Centauri does not have a net stretched across its orbital plane to catch incoming spacecraft. Deceleration is the hidden monster of interstellar mission design. It is the constraint that separates a flyby from an arrival, a photograph from an exploration, a stunt from a mission, and it roughly doubles the total energy requirement of the entire voyage. If your goal is simply to fly past the target star, take some pictures during the brief encounter window, and keep going into deep space forever, then you never need to slow down. This is the breakthrough starshot model. It is also the Daedalus model. Both were flyby missions. The spacecraft would scream through the Alpha Centauri or Barnard star system at 10 to 20% of light speed, getting perhaps a few hours of close observation before the target receded behind them at millions of miles per hour. For an uncrewed probe, this is acceptable. Data can be collected and transmitted back to Earth by radio or laser. The probe itself is expendable. For a crewed mission, this is not acceptable. You cannot send human beings on a 42-year voyage and then fly past the destination without stopping. The entire purpose of a crewed mission is to arrive, to enter orbit, to study the system up close, perhaps to land on a planet or moon. Arrival requires deceleration, and deceleration at interstellar speeds is almost as energy-intensive as acceleration. The physics is symmetric. To slow down from 10% of light speed to rest requires removing exactly the same kinetic energy that was added during acceleration. If the spacecraft uses its own engine to decelerate, it must carry enough fuel to perform the braking maneuver in addition to the fuel it already carried for acceleration. The rocket equation punishes this doubly, because the deceleration fuel must itself be accelerated during the first phase of the mission, which means you need even more acceleration fuel to carry the deceleration fuel. The total fuel requirement does not simply double, it compounds exponentially. For a fusion-powered spacecraft that needs a mass ratio of, say, 100 to 1 for acceleration alone, 100 kilograms of fuel per kilogram of payload to reach the target speed, adding deceleration capability pushes the mass ratio to roughly 10,000 to 1, 100 squared. For every kilogram of crew, life support and instruments that arrives at Proxima Centauri at rest, the ship must depart Earth carrying 10,000 kilograms. A crewed vessel with a modest payload of 100 tons at arrival would need to launch with 1 million tons of fuel. Some mission designs attempt to cheat the deceleration problem. One approach is magnetic braking, using a large magnetic sail to create drag against the interstellar medium or the target star's stellar wind. gradually slowing the spacecraft over years. This concept, sometimes called a magsail, was proposed by Robert Zubrin and Dana Andrews in 1990. It avoids carrying deceleration fuel but requires an enormous superconducting loop generating a magnetic field many kilometers in diameter, and the braking force is weak, meaning deceleration would take decades even with optimistic assumptions about stellar wind density. A ship approaching Proxima Centauri's relatively feeble stellar wind. Proxima is a low-mass red dwarf with a weaker stellar wind than the Sun, might not generate enough drag to stop within any reasonable time. Another concept proposes using the target star's light for braking. A laser sail that was accelerated by Earth-based lasers could, in principle, reconfigure its sail geometry to catch starlight from the destination star and use it for deceleration. Robert Forward proposed an elegant version of this in the 1980s, using a two-stage sail where the outer ring detaches and reflects laser light back onto the inner section, decelerating it. But this requires an impractically large sail and precisely coordinated maneuvers at interstellar distances, with no ground control possible due to the years-long communication delay. There is no easy way to decelerate at interstellar speeds. Every proposed method is either energy prohibitive, technologically immature, or dependent on environmental conditions at the destination that may not cooperate. This single constraint, the need to stop, transforms the interstellar travel problem from brutally difficult to something approaching physically intractable for crewed missions with current or near-future physics. And this distinction is precisely what separates probe missions from human missions in the most fundamental way. The gap is not merely one of scale, it is a gap in kind. A gram-scale probe does not need to decelerate, it does not need radiation shielding beyond minimal hardening of its electronics. It does not need dust protection beyond a small forward surface. It does not need life support. It does not need food, water, air, medical systems, psychological support, exercise equipment, or waste recycling. It does not need to survive for 40 years. It needs to survive for 20 years of coast and a few hours of data collection. It does not carry humans who age, who get sick, who need sleep, who experience loneliness and psychological breakdown. A crewed interstellar vessel is not a scaled-up version of a breakthrough Starshot chip. It is a fundamentally different engineering challenge. Every system on a crewed ship must function flawlessly for decades without resupply or repair from Earth. And it is here, in the realm of sustained human survival between the stars, that the problem acquires a weight that engineering diagrams alone cannot capture. The life support system must recycle air and water at near-perfect efficiency for 40 or more years. On the International Space Station, life support is maintained through a combination of onboard recycling systems and regular resupply missions from Earth. Cargo ships arrive multiple times a year carrying fresh water, food, spare parts, and replacement components for systems that wear out. An interstellar vessel has no resupply. Everything the crew will ever need must be on board at departure or manufactured during the voyage. The water the crew drinks in year 1 is the same water, recycled and purified and recycled again, that they drink in year 40. The air they breathe is the same air, scrubbed of carbon dioxide and replenished with oxygen by chemical or biological processes for the entire duration. Any failure in these systems that cannot be repaired with onboard materials is potentially fatal. A cracked seal in the water recycler, a degraded catalytic bed in the carbon dioxide scrubber, a contaminated oxygen supply. On the space station, these are maintenance events. On an interstellar ship, they are existential crises. Food must either be grown on board, which requires agricultural systems, lighting, soil or hydroponic infrastructure, and redundancy against crop failure, or carried in preserved form, which adds thousands of kilograms of mass. Growing food for a crew of even 6 people for 40 years demands a farming operation of surprising scale. Estimates for closed-loop agricultural systems capable of sustaining a small crew suggest cultivation areas of several hundred to over 1,000 square meters, incorporating grains, legumes, vegetables, and possibly algae or insect protein. These farms must be lit artificially, irrigated from the recycled water supply, and protected from the same radiation environment that threatens the crew. A single crop blight, a mold contamination, a lighting system failure lasting more than a few weeks could destroy the food supply and starve the crew years before arrival. Carrying preserved food as a backup adds enormous mass, and preserved food degrades over decades even under ideal storage conditions. Medical emergencies must be handled by the crew themselves, with no possibility of evacuation. A burst appendix, a cancer diagnosis, a compound fracture, a dental abscess, all must be treated on board with whatever equipment was loaded at departure. The crew would need to include individuals trained in surgery, dentistry, pharmacology, and emergency medicine, or possess medical robots capable of performing these functions autonomously. Over a 42-year span, the statistical likelihood of serious medical events across a crew of 6 to 12 people is not small. Heart attacks, strokes, infections, and injuries are near certainties over that timescale. On Earth, any of these conditions can be treated with hospital infrastructure. Between the stars, the hospital is whatever fits inside the ship. There is no medevac. There is no second opinion from a specialist. There is no ambulance. The psychological dimension is equally severe and perhaps less solvable than any of the physical challenges. A crew of astronauts confined to a spacecraft for 42 years would experience isolation beyond anything in human history. The current record for continuous spaceflight is roughly 437 days, held by Valery Polyakov aboard the Mir space station in 1994 and 95. Extending that to 42 years, approximately 35 times longer, introduces psychological stresses that we have no experimental basis for predicting. Long-duration isolation studies on Earth, such as the Mars 500 experiment in Moscow, which confined 6 volunteers for 520 days, reported significant psychological effects including depression, sleep disorders, and interpersonal conflict, and that was with the knowledge that the experiment would end and the participants would return to normal life. The participants knew every single day that they could walk out if a genuine emergency arose. They knew the experiment had an end date. They knew their families were a phone call away. An interstellar crew would have none of these comforts. They would know with certainty that they would spend the majority of their remaining lives inside the ship. They would know that they could never return home within their lifetimes unless the mission included a return trip which would double the voyage time to 84 years. Consider what 42 years means in human terms. It is the span from a young adult's mid-20s to their late 60s. During those decades on Earth, a person might marry, raise children, watch those children grow into adults, change careers multiple times, lose parents, gain grandchildren, and experience the full arc of a middle life. On the ship, none of this happens in a normal way. Relationships form within a group so small that interpersonal friction has no outlet. Children, if born, grow up knowing no world except the interior of the vessel. Aging occurs in confinement. Grief happens without the support of extended family or community. Boredom becomes not an inconvenience but a chronic psychological threat spanning decades. The human mind did not evolve for this. It evolved for open landscapes, for social groups numbering in the dozens to hundreds, for variety, novelty, seasonal change, and the possibility of movement. Strip all of that away for 42 years, and you are conducting a psychological experiment with no precedent and no safety net. Communication with Earth would be possible but subject to enormous delays. At the midpoint of the journey, roughly 2 light years from both Earth and the destination, a message sent to Earth would take 2 years to arrive, and the reply would take another 2 years. A 4-year round-trip delay makes real-time conversation impossible. The crew would be functionally alone, exchanging messages that are always years out of date. Loved ones would age, political situations would change, cultural references would shift, and the crew would become increasingly disconnected from the civilization that launched them. By the time the crew arrives at Proxima Centauri, nearly half a century of human history will have unfolded on Earth without them. The world they left will no longer exist in any recognizable social or cultural form. They will arrive as strangers to their own species, carrying memories of a world that has moved on without them. Then there is biological aging. This is the constraint that most directly answers our central question. At 10% of the speed of light, the relativistic time dilation factor, described by the Lorentz factor from special relativity, is approximately 1.005. This means that time aboard the ship passes about 0.5% slower than time on Earth. Over a 42-year journey, the crew would experience roughly 41.8 years instead of 42, a savings of about 2.5 months. This is real but negligible. It does not meaningfully extend the crew's lifespan or compress the mission duration. Time dilation only becomes significant at much higher velocities. At 50% of the speed of light, the Lorentz factor is about 1.15, compressing a 42-year Earth time journey to roughly 36.5 years of shipboard time. At 90% of light speed, the Lorentz factor is approximately 2.3, and the same Earth distance journey would feel like only about 18 years to the crew. At 99% of light speed, the factor rises to about 7, and the trip would feel like only 6 years. These numbers sound encouraging until you remember what achieving those speeds requires. 90% of light speed demands roughly 81 times more kinetic energy than 10% of light speed, because energy scales with the square of velocity, and at these speeds, relativistic corrections make the scaling even steeper. 99% of light speed requires a Lorentz factor so high that the effective mass of the spacecraft increases 7-fold, demanding energy inputs that are difficult to express in meaningful terms. No proposed propulsion system, not fusion, not antimatter, not laser sails, comes close to accelerating a crewed vehicle to these speeds. Time dilation is a real physical effect, confirmed by countless experiments, but it only helps travelers who can reach speeds that no crewed ship can plausibly achieve. So the crew ages. They age at essentially the normal rate, because the speeds that would compress their subjective time are far beyond what any crewed vessel could reach. A 25-year-old who departs for Proxima Centauri at 10% of light speed arrives as a 67-year-old. If the mission includes any deceleration phase, which adds years, the arrival age climbs higher. If the mission is a round trip, the traveller returns to Earth at approximately age 109, assuming they survive the journey at all. Even with optimistic projections for human life extension, a round trip to the nearest star at 10% of light speed consumes an entire human life. This is the biological wall. You cannot negotiate with it. You cannot engineer around it. You can only go faster, and going faster multiplies every other problem: radiation, dust, energy, shielding, fuel, by factors that are already at the limits of physical possibility. The alternative to solving all of these problems simultaneously is to abandon the one-lifetime constraint entirely and accept that interstellar travel, if it happens at all, will be a multi-generational endeavour. This is the concept of the generation ship, a vessel large enough to sustain a self-sufficient human community for centuries, with successive generations being born, living, and dying aboard the ship during the long transit between stars. The generation that departs is not the generation that arrives. The mission spans many lifetimes, not one. Generation ships solve the biological aging problem by redefining the mission. If no individual needs to survive the entire journey, the speed requirement drops dramatically. A generation ship travelling at even 1% of light speed, roughly 3,000 kilometers per second, would reach Proxima Centauri in about 424 years. That is a long time, but it is not 73,000 years. It is comparable to the time since the European Renaissance. Quote, "A community that departed in the 1600s, by this analogy, would arrive today, difficult, but conceivable in terms of social continuity. However, generation ships introduce their own catastrophic set of problems. The vessel must be essentially a self-sustaining world, a closed ecosystem that recycles all resources indefinitely. It must maintain genetic diversity across a population large enough to avoid inbreeding depression over dozens of generations. Estimates suggest a minimum viable population of at least several hundred to several thousand individuals. The ship must therefore support not a handful of astronauts, but a small city with all the agricultural, industrial, medical, educational, and governance infrastructure that implies. The mass of such a vessel would be millions of tons at minimum, driving the propulsion and energy requirements to levels that make even a single crew interstellar mission look modest by comparison. The sociological challenges are equally formidable, and in many ways less tractable than the engineering ones, because they involve predicting the behavior of human societies across timescales that exceed the lifespan of most earthbound institutions. How do you maintain a coherent mission purpose across 20 generations of people who never chose to be on the ship? The founders who departed Earth had a reason, a vision, a destination. Their children grew up hearing stories of that vision. Their grandchildren inherited it as tradition. But what about the 10th generation, the 15th, the 20th? By that point, the original purpose is as remote as the myths of ancient civilizations are to us. The destination is something their ancestors chose. The ship is the only world they have ever known. Why should they care about arriving somewhere they have never seen, based on a decision made by people who died centuries ago? How do you prevent social collapse, civil conflict, or authoritarian drift in a closed system with no external check on power? On Earth, tyrannical governments eventually fall because populations can flee, resources can be contested, and outside pressures force change. On a generation ship, there is no outside. There is no refuge. There is no emigration. A governing faction that seizes control cannot be overthrown by appealing to neighbouring states for support, because there are no neighbouring states. The ship is the entire political universe. History suggests that closed, isolated communities with absolute authority structures tend toward dysfunction, stagnation, or collapse. Maintaining a healthy, democratic, adaptable society for 400 years in a sealed metal cylinder hurtling through the void is a challenge that makes the propulsion problem look straightforward by comparison. How do you ensure that the technical knowledge needed to operate the ship and execute arrival maneuvers is preserved across centuries without institutional decay? The crew that departs Earth includes trained engineers who understand every system on the vessel. Their children will learn from them. But knowledge transmitted across generations without external institutions, without universities and libraries and professional societies with their own continuity, has a tendency to degrade. Skills that are not practiced are lost. Understanding that is not refreshed by new discovery becomes dogma. By the 20th generation, the crew may be operating equipment they no longer fully understand, following procedures that have been copied and recopied with accumulating errors. A critical system failure in Generation 15 that requires adaptive engineering, not just rote maintenance, could doom the mission if the knowledge base has eroded too far. These are not engineering problems. They are problems of human nature, and human nature has a poor track record of maintaining stable institutions over centuries even on Earth, where the stakes are lower and alternatives exist. Generation ships are a legitimate concept, and they may ultimately be the only realistic path to interstellar colonization. But they do not answer our central question. They explicitly reject the premise. The question is whether a human being can reach another star in one lifetime. A generation ship says no individual can, but a lineage might. That is a different answer to a different question. Every path we have examined, every technology we have evaluated, every physical constraint we have calculated, leads to the same tightening vice. The distance is too great for current speeds. The speeds required demand energy beyond civilization scale output. Even if speed is achieved, radiation and dust threaten to destroy the ship. Even if shielding is solved, deceleration doubles the energy problem. Even if deceleration is solved, the crew ages through the entire voyage with negligible help from time dilation. Even if aging is accepted, The psychological and life support burdens of a multi-decade voyage in deep space are unprecedented and untested. And if you abandon the single lifetime constraint, you enter the domain of generation ships, which require building self-sustaining worlds in space, a challenge arguably greater than the propulsion problem itself. The constraints do not operate independently, they compound. Solving one often worsens another. More shielding means more mass, which means more fuel, which means a larger ship, which means more life support, which means more mass, which means more fuel. The feedback loops are vicious and they all push in the same direction, toward missions of such scale and complexity that they exceed the capability of any civilization that currently exists or is likely to exist in the near future. We have now laid out every major physical, engineering, and biological constraint that stands between a human being and the nearest star. The question that remains is the one we started with. After all of this, what is the honest answer? Can it be done? And if not now, then when? And if not when, then what does that mean? We have walked through every layer of the problem. We measured the distance, we calculated the speed, we confronted the energy. We examined the shielding, the dust, the radiation, the deceleration, the biological clock, the psychological isolation, the life support burden. Each layer made the answer harder. Each constraint reinforced the last. Now it is time to assemble the full picture and deliver the verdict that the question deserves. Could a human being leave Earth, travel to another star, and arrive alive within a single lifetime? Let us restate the constraint stack in its entirety, because the cumulative weight matters more than any single barrier. The nearest star, Proxima Centauri, is 4.24 light-years away. That is approximately 25 trillion miles. At the speed of our fastest outbound spacecraft, Voyager 1, the journey takes roughly 73,000 years. To compress that journey into a human lifetime of 80 years requires a minimum average speed of about 5% of the speed of light. To allow a more practical voyage of 40 years with the astronaut arriving in functional health, the required speed rises to approximately 10% of light speed, or 67 million miles per hour, roughly 1,760 times faster than any spacecraft we have ever sent beyond the solar system. Achieving that speed demands energy inputs that dwarf anything our civilization currently produces. Chemical propulsion is categorically incapable of reaching even 1% of light speed. Nuclear thermal propulsion cannot do it. Nuclear pulse propulsion, the concept behind Project Orion, could theoretically reach a few percent of light speed, but has never been tested and faces legal, political, and engineering barriers that have prevented development for over 60 years. Fusion propulsion could theoretically push an uncrewed probe to 10 or 12% of light speed, but no sustained controlled fusion engine exists in any form, and the fuel requirements for a crewed mission would run to tens of thousands of tons of helium-3, a substance that would need to be harvested from the atmosphere of Jupiter. Antimatter propulsion offers the highest theoretical performance of any concept permitted by known physics, but humanity currently produces antimatter in quantities measured in nanograms per year, at costs that exceed the gross domestic product of nations for even a single gram. Scaling to the kilograms or tons needed for an interstellar mission is not a foreseeable engineering milestone. It is a fantasy measured in centuries of required progress. Laser sail propulsion, the concept behind breakthrough Starshot, elegantly sidesteps the fuel problem by keeping the energy source on the ground, but it works only for spacecraft weighing grams. Scaling the concept to a crewed vessel weighing tens of thousands of kilograms or more would require laser arrays with power outputs trillions of times greater than those envisioned for the already stalled Starshot program. The gap between accelerating a postage stamp-sized chip and accelerating a vessel carrying living humans is not a matter of degree. It is a difference so vast that the two problems share almost nothing in common except the word spacecraft. Even if propulsion were solved, the voyage itself presents lethal hazards. The interstellar medium, though sparse, becomes a torrent of high-energy particles relative to a ship moving at 10% of light speed. Hydrogen atoms that are harmless at rest become penetrating radiation at relativistic velocities, delivering lethal doses to unshielded crew within days to weeks. Interstellar dust grains weighing less than a millionth of a gram strike with the energy of substantial explosives, each individual particle capable of breaching an unprotected hull. Shielding against these threats requires either massive physical barriers or active deflection systems, both of which add weight that compounds the already crushing fuel problem through the exponential mathematics of the rocket equation. Deceleration, the requirement to actually stop at the destination rather than fly past it, roughly doubles the total energy budget. A flyby is one thing, an arrival is another. For a crewed mission, arrival is the entire point. But the fuel needed to slow down must be carried from the start and itself accelerated to cruising speed, creating a compounding mass penalty that pushes fuel ratios from the merely enormous into the structurally impossible. Every proposed deceleration method for crewed interstellar travel, whether onboard propulsion, magnetic braking against stellar winds, or reflected light sail maneuvers, is either energy prohibitive, technologically undemonstrated, or dependent on environmental conditions at the target system that may not be sufficient. The crew ages. At 10% of light speed, relativistic time dilation is negligible, compressing a 42-year journey by only a few months. Time dilation becomes meaningful only at speeds above 50% of light speed, and significant above 90%. But reaching those velocities multiplies the energy requirement by factors of dozens to hundreds, pushing every other constraint further beyond the bounds of feasibility. There is no relativistic shortcut available at any speed a crewed vessel could plausibly reach. Life support must function perfectly for decades. Air and water must be recycled with near total efficiency. Food must be grown or carried in quantities that add thousands of kilograms of mass. Medical emergencies must be handled without external aid, with a communication delay to Earth measured in years. Psychological endurance across a multi-decade voyage in confinement, with no possibility of rescue and no certainty of return, exceeds any isolation ever experienced or experimentally simulated by human beings. This is the full constraint stack. Not one barrier but many, layered on top of each other, each one reinforcing the rest. Solving the propulsion problem does not solve the shielding problem. Solving the shielding problem does not solve the deceleration problem. Solving the deceleration problem does not solve the life support problem. And solving all of them simultaneously does not change the fact that the crew will age through the entire voyage with almost no help from the physics of time dilation. So what is the honest answer? With any technology that exists today, the answer is no. Not close to yes. Not maybe in a few years. No. Definitively, unambiguously, no. Nothing we currently possess or are building, or have funded, or have planned, can send a human being to another star and bring them into orbit before they die. The gap between our current capability and the minimum requirement is not a gap that improved engineering can bridge in the near term. It is measured in orders of magnitude across multiple independent variables simultaneously. With technology that might plausibly exist within the next century, the answer remains almost certainly no. Fusion propulsion, if successfully developed for spaceflight, might eventually push uncrewed probes to 10 or 12% of light speed. But a crewed vessel with life support, shielding, and deceleration capability is a fundamentally different machine. Scaling from a probe to a crewed ship multiplies mass by factors of thousands, and the rocket equation punishes every additional kilogram with exponential fuel penalties. Even optimistic projections for fusion technology do not overcome this scaling barrier within any timeline that current physics and engineering practice can support. Could the answer change further in the future? Yes. In principle, yes. Physics does not forbid a human being from reaching another star within a lifetime. The speed of light is not the barrier. We do not need to reach light speed. We need perhaps 10 to 20% of it, and while the energy required is colossal, it is finite. The laws of thermodynamics and relativity do not contain a clause that says thou shalt not cross interstellar space in 80 years. The prohibition is practical, not fundamental. The energy exists in the universe. The physics allows the speed. What does not exist is the technology to harness that energy and apply it to the problem at a scale compatible with human survival. A breakthrough in any of several areas could, in principle, change the calculation. If controlled fusion becomes routine and compact, producing engines with exhaust velocities of tens of thousands of kilometers per second, the propulsion barrier drops. If antimatter can be produced in bulk at costs many orders of magnitude below current levels, perhaps through entirely new production methods that no one has yet conceived, the energy density of fuel ceases to be a limiting factor. If materials science produces shielding that is both lightweight and capable of absorbing relativistic particle impacts, the mass penalty of protection shrinks. If artificial hibernation or suspended animation becomes medically possible, allowing crew members to sleep through decades of transit with minimal aging, the life support and psychological barriers diminish dramatically. Each of these breakthroughs is individually plausible at some point in the far future. None is guaranteed. None is on a timeline, and the interstellar problem requires not one of them, but several operating in concert, because the constraint stack is not a single wall. It is a series of walls, each behind the last, and clearing one only reveals the next. It is also worth stating clearly what kinds of breakthroughs would not help. Faster computers will not help. Better software will not help. Advances in artificial intelligence, however dramatic, will not help with the fundamental energy and mass constraints of propulsion. More efficient solar panels will not help, because the sunlight available in interstellar space is negligible. Improvements in rocket nozzle design will not help, because the limitation is exhaust velocity and fuel energy density, not mechanical efficiency of the engine. Better telescopes will not help the travelers get there. They will only show us more clearly what we are missing. The specific class of breakthroughs required is narrow. Energy production at scales far beyond current capability. Propulsion physics with exhaust velocities orders of magnitude beyond any demonstrated system. Materials science capable of containing and directing the extreme energies involved. Biological science capable of sustaining or pausing human life for decades. These are not incremental advances. They are revolutions in fundamental capability, the kind that tend to arrive on timescales of centuries rather than decades, if they arrive at all. There is one additional category that deserves mention, not because it is plausible, but because it is frequently invoked: new physics. The discovery of some principle or mechanism that is not currently known, that would allow manipulation of space-time, inertia, or energy in ways that present physics does not permit. Warp drives, wormholes, inertial dampeners. These concepts exist in the mathematical frameworks of general relativity and quantum field theory, but only as speculative solutions with no experimental support. We discussed warp drives and wormholes in detail earlier. Nothing has changed. They remain speculative mathematical constructs with no experimental support and no pathway to physical realization. Hoping for new physics is not a plan, it is a wish. It might come true. It has no timeline. It cannot be relied upon. So the answer, stated with full honesty, is this. A human being reaching another star within a single lifetime is not physically forbidden, but it requires technological capabilities so far beyond what currently exists that no responsible assessment can assign a timeline. It is not a problem that will be solved by the next generation of spacecraft or the generation after that. It is a problem that may take centuries of foundational scientific and engineering progress to become tractable, and it is possible, though not certain, that some of the required breakthroughs will never come. This answer is not despair, it is clarity. There is an enormous difference between saying something is impossible and saying something is extraordinarily difficult. The laws of physics permit interstellar travel at a fraction of light speed. Nothing in Einstein's equations says you cannot do it, but the practical barriers are so severe, so numerous, and so mutually reinforcing that clearing them represents one of the greatest challenges conceivable for a technological civilization. Perhaps the greatest. It is worth pausing here to notice what this question has taught us, because the value of asking whether a human can reach another star in one lifetime is not just in the answer, it is in what the question reveals about the universe we live in. The nearest star is visible to telescopes. Its planets can be studied. In August of 2025, the James Webb Space Telescope produced direct imaging evidence for a candidate giant planet in the habitable zone of Alpha Centauri A, a sun-like star, only 4.37 light-years away. We can characterize the atmospheres of worlds in that system. We can measure the masses and orbits of its planets. We may, within decades, detect biosignatures in the spectra of those atmospheres, chemical evidence of life. The nearest stellar neighborhood is not unknown. It is being mapped in extraordinary detail by instruments that grow more powerful each year. And yet we cannot go there. We can see it. We can study it. We can learn more about it than any previous generation imagined possible. But we cannot touch it. The gap between observation and visitation, between knowing and going, is not a gap of knowledge. It is a gap of energy, speed, and survival. It is a gap imposed by the sheer physical scale of interstellar space. This gap is itself a profound piece of information about the universe. It tells us that the cosmos is structured on a scale that dwarfs biological life. The distances between stars are not arbitrary. They are set by the physics of star formation, the distribution of matter in the galaxy, and the gravitational dynamics that space stellar systems apart from one another. The result is a universe in which stars are close enough to see, but too far to reach, at least within the timescale of a single biological life. This is not a coincidence. It is a consequence of the same physical laws that created the stars in the first place. The dream of reaching another star in one lifetime is ultimately a confrontation with the scale of the cosmos measured against the scale of a human life. 80 years is a long time by human standards. It is long enough to build civilizations, raise families, create art, develop technology, and fundamentally reshape the surface of a planet. But 80 years is nothing against the distances between stars. Light itself, the fastest thing the universe permits, needs more than 4 years to cover the distance to our nearest neighbor. A human life is roughly 20 times longer than the light travel time. That sounds like a comfortable margin until you realize that no crewed vehicle can come anywhere close to light speed, and the fraction of light speed that might be achievable requires energy, shielding, and engineering capabilities that do not yet exist. The universe is not hostile to interstellar travel. It does not actively prevent it. It simply does not accommodate it at the pace of human biology. The stars are separated by distances that are vast compared to a lifetime, but minuscule compared to the age of the galaxy. The Milky Way has existed for roughly 13 billion years. The light travel time to Proxima Centauri is 4.24 years. The galaxy has had 3 billion times longer than that light travel time to evolve. On galactic timescales, the nearest star is right next door. On human timescales, it is almost unreachably far. This is the true nature of the interstellar problem. It is not a problem of technology, although technology is necessary. It is not a problem of will, although will is necessary. It is a problem of mismatch between the timescale of a human life and the spatial scale of the cosmos. We are biological creatures who live for decades, trying to cross distances that take years at the fastest speed the universe permits. The mismatch is inherent. It is built into the fabric of physical reality, but it is not permanent, or at least it does not have to be. Human biology may change. Life extension, genetic modification, or artificial hibernation could stretch the effective duration of a human life far beyond its current limits. A human being who could remain healthy and conscious for 500 years would find a 50-year interstellar voyage a manageable fraction of their existence. A human who could enter suspended animation and awaken at the destination would experience the journey as a sleep. These possibilities are speculative today, but they are rooted in biology rather than physics, and biological barriers have historically proven more flexible than physical ones. Alternatively, the definition of what counts as reaching another star might evolve. If a human consciousness could be transferred to a digital substrate and transmitted as information, the journey could be accomplished at the speed of light, arriving at the destination in 4.24 years with no fuel, no shielding, and no life support. This concept raises profound philosophical questions about identity, continuity, and what it means to be human. But it also suggests that the interstellar travel problem might ultimately be solved not by building faster ships, but by reimagining what a traveler is. These are long-horizon possibilities. They do not change the near-term answer. They do not make the journey feasible today or tomorrow or in a century, but they gesture toward a future in which the question we have been asking might be reframed in ways that make the answer different. Not because the universe became smaller, but because we became something other than what we are now. For the present, and for the foreseeable future, the situation is this. We can send information to another star. Radio waves and laser pulses travel at light speed and reach Proxima Centauri in 4.24 years. We can almost certainly, within the next few decades to century, send tiny robotic probes to another star if concepts like laser sail propulsion are developed to maturity. Gram-scale chips traveling at 10 to 20% of light speed could reach Alpha Centauri in 20 to 40 years and transmit data back to Earth within a human lifetime. This is achievable in principle, though the engineering challenges remain formidable and the most prominent attempt, Breakthrough Starshot, has stalled. We cannot, with any existing or near-term technology, send a living human being to another star and have them arrive alive. The energy required is too vast. The speeds demanded are too extreme. The hazards of the interstellar medium are too severe. The deceleration problem is too punishing. The biological clock is too relentless. Each barrier alone is daunting. Together, they form a wall that no technology on any current development trajectory can breach. Reaching another star in one lifetime is not just a matter of building a better ship. It requires confronting some of the hardest limits in physics, engineering, and human survival, simultaneously, without compromise, across every dimension of the problem. It requires energy on a scale that challenges the output of civilizations. It requires speeds that turn empty space into a lethal environment. It requires the human body to endure decades of isolation and confinement with no margin for error. It requires stopping at the destination, which demands as much energy as getting there in the first place. And it requires all of this to work in concert, flawlessly, across a span of time longer than most nations have existed. This is what the dream actually costs. Not money, not political will, not imagination. Physics. The dream costs more physics than we currently know how to pay. And yet the dream is not worthless. The value of an unanswerable question is that it tells you exactly how far you have to go. The interstellar travel problem is a mirror. It shows us with terrible precision where the edge of human capability lies. Not at the moon, which we reached over half a century ago. Not at Mars, which we might reach within decades. The edge is between the stars. That is where ambition collides with the structure of the universe and discovers that the universe is larger than ambition. Proxima Centauri sits 4.24 light-years from where you are right now. If you went outside on a clear night and looked toward the constellation Centaurus, you would not see it because it is too faint. But it is there, a dim red star smaller than our Sun, flickered with violent flares, orbited by at least 2 confirmed planets, one of them roughly the size of Earth and sitting in the habitable zone. It is the closest other sun in the galaxy. It is our nearest neighbour in a cosmos of 400 billion stars, and it may remain beyond human reach for a very long time. Not because we lack courage, not because we lack curiosity, but because the universe is built on a scale that does not bend to either. The space between the stars is not a barrier placed there to test us. It is simply the size of things. It is the distance that the physics of star formation and galactic dynamics has placed between one sun and the next. It is not personal. It is not deliberate. It is just vast. 25 trillion miles. That is the distance to the nearest star. At our best speed, 73,000 years of travel. At the speed required for a one-lifetime journey, an energy investment larger than anything our civilization has ever produced for any purpose. At the speed that would make time dilation actually help, an energy requirement that enters the realm of the mathematically expressible but physically unimaginable. The stars are right there. We can see them. We can name them. We can count their planets. We can model their atmospheres. We can dream of standing on their worlds. We just cannot get there yet, and the distance between yet and now may be measured not in years of engineering but in revolutions of understanding that no one alive today can predict or schedule. That is the honest answer. That is what the question really means, and that is the cost of the dream.